Hello guys, nice to see you. How are you doing after fall break?
Good afternoon.
Hi.
Hello. Good afternoon.
Hello. Nice to see you. Okay, so before this fall break, we finished one of our topics, which is gravity. And now we proceed further. So we will consider our next topic is oscillations, mechanical waves. So we will start from simple harmonic oscillation, general equations for the simple harmonic equation for the displacement as a function of time, velocity, and acceleration of as a function of time of a particle which undergoes simple harmonic oscillation. That will be pretty much our discussion for today. So I think we can switch to the slides and start deriving, like first describing the particular system which we are going to consider, and then deriving all these mentioned equations. Okay. So in general, we can consider some like oscillations as periodic motion, and periodic motion is some repeating motion of an object when it comes back to, like, returns to a given position after a fixed time interval. So it means there is some period of this periodic motion, and within this fixed time interval, which is period, the object or particle will always come back to this given position. The most general case, which is some building block of all periodic motions, is simple harmonic motion. That's what we are going to focus our attention during this discussion the most. So let us consider some ideal system which will be the best for studying simple harmonic motion. And such system is some isolated spring block system. So when we have some block attached to a spring, let us consider that our string is stretched at t equals to 0. Let's consider this is our equilibrium condition. X is x. This is displacement 0. So at t equals 0, we have some positive displacement a. And this is mass of the block. And obviously, this spring will possess some spring constant, like coefficient k. We know that if we out of equilibrium condition with such system, there will be some spring force. So spring force, Fs, is equal to minus kx. So in this case, spring force will be pointed to the left, Fs. And if we come back upon the action of this spring force to the equilibrium condition, then spring force will be equal to 0. There's no displacement, no spring force. And then if the spring is compressed, so we assume that there are no dissipation, there's no dissipation of mechanical energy because of friction or something like that. So it could be considered as minus A here. Then we have spring force acting already from on this block with mass m, and it's pointed from the left to the right. So if we recall second law of motion, we can write that minus k times x, like force which acts on the block, is equal to the mass of its block times acceleration. So now we consider one-dimensional case, it's acceleration along axis x. So we can express acceleration from previous equation. It will be minus k divided by m times x. So what this equation tells us, that acceleration is proportional to displacement, and it is pointed in the opposite direction as the displacement. So acceleration vector is pointed in the opposite direction as displacement vector because we have this sign minus here. So this is like mandatory conditions for realization of a simple harmonic motion. Our task is to find, like, first step, to find displacement, like position of this block x as a function of time. That will be equation of the simple harmonic motion. So any ideas how we come to this point? How can we get x as a function of time? Acceleration, what is this? How can we relate acceleration and this function, x as a function of time?
To find the integral, or?
Depends what you are doing, but let's say if we have this function, x as a function of time, so we can take second derivative of this function over time, and that will give us acceleration. So means that acceleration, we can also write that it will be dx d square x over dt square. So yeah, and then if we know acceleration, we can integrate, applying some boundary conditions, and get x as a function of t, which actually exactly what we are going to do now, because we know acceleration, we know how acceleration depends on this position x. So we will use this information in order to get a known function x as a function of t.
Professor, excuse me, can you hear me?
Yes, sure.
I guess x as a function of t should be some trigonometric function like sinus of omega t plus phi, where phi is like the initial phase. Am I right?
Yeah, you are right. And I think that here we will go step by step the derivation. We will have differential equation. We will solve this differential equation, apply boundary conditions, and we will come to this equation which you mentioned. You are absolutely
okay.
But we will see where it comes from, and of course then we'll consider what does it mean and what it brings us. So we can just equate this second derivative and this equation. So it will be d square x over dt is equal to minus k mx. Or we can rearrange it. So let's put it right side to the left. It will be d square x over here dt square plus k divided by m times x, and that is equal to 0. So now we have a differential equation, and you don't need to be a genius mathematician to invent from scratch solutions of differential equations. Everything what you need to do, those who are not professional mathematicians, you need to first identify which type of differential equations is that equation which you deal with. So in this particular case, this is second order linear differential equation. Second order because we have second derivative of unknown function x. So in order to solve such differential equation, this type of differential equations, you can just check the rules, and they will tell you that it's necessary to build some characteristic equation where first derivative of unknown function will be considered as some parameter lambda, characteristic parameter lambda. So now we can rewrite this in terms of this characteristic parameter lambda, and that will be lambda squared because we have second derivative plus k divided by m that equals to 0. And we solve this characteristic equation. It's some quadratic equation. So let us write it here on this other slide. Lambda squared plus k divided by m equals to 0. We know the general case of quadratic equation from school looks like this. We have a, let's consider lambda as our unknown. So it will be lambda squared plus b lambda and plus c equals to 0. Yes, there is some question.
Excuse me, why we didn't write the x in this equation? I'm a little bit confused about it.
Yeah, so it is about characteristic, it's characteristic equation which takes into account the derivative of dx over dt. If we don't have it, we don't consider because it's here is kind of like a function itself, this x. So we consider only coefficient next to this function. And then we have derivative, second derivative is lambda squared plus coefficient next to the function itself. Yeah, that's the rule for forming this characteristic equation when you take into account only lambda, which is first derivative over t, or lambda squared, which is second derivative over t. And then next to the function itself, x, we only take into account the coefficient. So don't really ask me why it's like this. There are rules for different types of differential equations, and that helps to have some uniform approach to solve them. Can really look a bit deeper into that, but I believe that more specifically, like some professor of mathematics can explain definitely better how this works specifically for this second order linear differential equation. But we follow the procedure of getting the characteristic equation and solve it. Based on the solution of characteristic equation, we will see which type of equation will satisfy the solution of this differential equation, which we are trying to solve.
Okay, thank you.
You're welcome. So now we see that this coefficient A, in our case, is unity. Coefficient B, we don't have first derivative in our equation, because in general, it could be second order linear differential equation more complicated than ours, because we could have second derivative, first derivative, and the function itself. So we don't have that, and that B is equal to 0, and C is equal to this K divided by M. Okay, how do we solve quadratic equation? That's general. Let's go for general case. We have discriminant. That is in general case B square minus 4AC. Taking into account values for our coefficients, we get that our discriminant will be equal minus 4 times K divided by M. So now in the next step, we get expressions for the solutions of this equation. We have quadratic equation, we have two solutions. Now 1 and 2. That will be minus the general case, minus B plus minus square root of the discriminant divided by 2A. So that will result in plus minus square root of 4 times K divided by M divided by 2, because A is unity. So we take out from the square root our 4. Then we cancel it with the 2 in denominator. So that's why we have plus minus square root. Sorry, here we should have minus. We have minus here. So it will be minus K divided by M. Since we have minus under square root, means that we deal with complex numbers. And that's why our solution can be in correct form represented as I times square root K divided by M, where I stands for this imaginary unit. That is square root minus unit of minus unity. So according to these rules for solving second order differential equations, linear differential equations, if our solution of the characteristic equation is a complex solution, then the form of the equation which will satisfy our differential equation as a solution should be the following. So it's x as a function of t should be given in the following form. Constant 1 times cosinus square root of the numerical value of this complex solution of the characteristic equation, which is k divided by m plus, and also multiply time t, plus constant 2, C2, times sinus square root of this numerical value, k divided by m, times t. So that already you can see from where this sinus and cosinus is coming from. That's a general form for solving such this type of differential equation, which we build we form based on the system which we consider, applying second law of motion and considering expression for the spring force. So now we definitely need to do additional steps because these two constants are unknown. And in order to get final form, explicit form for the simple harmonic motion of our particular block attached to the particular string, we need to apply boundary conditions. So first boundary condition, let us maybe come back to this figure. We know that at t equals 0, our block is at position +8. So we can write here that at t equals 0, x is equal to capital A. So this is our first boundary condition. Let us apply this boundary condition. So it will be A instead of x equals to C1 times cosinus 0, because t is equal to 0, plus C2 times sinus 0. Sinus 0 is equal to 0, and cosinus 0 is equal to unit. From here, we can show that C1 is equal to A, because sinus 0 is 0, so C2 will be automatically cancelled out. So we know already the first constant, and now we need to get the second one. Any ideas which second boundary condition we can use at t equals 0?
Acceleration equals 0.
Acceleration, yeah, but close, but it's a bit, there is an easier option than acceleration. There is velocity. We know that we start from this t equals 0, it goes to maximum displacement, and that moment it doesn't move. So when time starts, the system starts to oscillate. But at t equals 0, we can write that velocity, which is the first derivative of the displacement over time, is equal to 0. So what we need to do now, we need to take derivative of this general form of the solution and set it to 0 at t equals to 0. Then we will have a chance to get the value of second constant C2. So let us maybe write on the next slide this general form x as a function of t, and then we will take first derivative over time. So that will be x as a function of t is equal to C1 times cosine, yes, cosine square. Oh, another thing what is good to do in order to make our life a bit easier. Let's make substitution that omega is equal to square root of k divided by m. So it's actually omega stands for angular frequency. Then we can write here omega t, cosine omega t plus C2 times sinus omega t. So it's the same equation as previous one, as this one. But instead of square root of k divided by m, we put omega. So this is our substitution. So now we take first derivative of dx over dt. That is equal to C1. We remember that derivative of cosinus gives us minus sinus, and derivative of sinus gives us cosinus. So that will be minus here. Here will be sinus omega t. And since we in the argument of sinus, we have this omega t, we need to take derivative of this argument and multiply also. So that will be times omega plus C2 times cosinus omega t and times omega. Okay, so now we set the condition that at t equals to 0, we have dx over dt is equal also to 0. So we can write 0 is equal to minus C1 sinus omega t times omega. Sorry, not omega t, but 0. We set t is equal to 0 plus C2 times cosinus 0 times omega. Okay, now we have this situation. Here is equal, sinus 0 is equal to 0, cosinus 0 is equal to unity. Since omega is not equal to 0, because we need to have some frequency of oscillation of this harmonic motion, if it happens, then there is only one option to get 0. C2 should be equal to 0. So now we have the second constant defined. So if we substitute first and second constant into this general form of solution, and these constants are determined based on our boundary conditions of the particular system we consider, then we will get x as a function of time, which is equal to a, amplitude of the displacement, times cosinus omega t. As you mentioned at the beginning, there should be some plus phi. So that is more general form. So because this solution is explicitly for our case, when at t equals to 0, x is equal to amplitude value. However, as you can imagine, this simple harmonic motion process can start from any initial displacement when x is not exactly equal to the amplitude value. In order to take that into account in this general equation, we can write that x as a function of t is equal to amplitude times cosinus omega t plus phi. And phi here stands for the phase constant. So it shows at which phase our like motion, this simple harmonic oscillation started. And this omega t plus phi gives us the phase of the simple harmonic motion. So now, once we have already general equation which describes displacement as a function of time, x as a function of t, we can proceed further based on our previous experience with kinematics. We can take first and second derivative of this equation over time and get expressions for the velocity as a function of time and acceleration as a function. So let us do it on the next slide. So here is x as a function of t is equal to a times cosinus omega t plus phi. So that is our simple harmonic motion equation. V as a function of t, velocity, is first derivative of displacement over time, and that will be minus. We will have this omega from the argument of cosinus times a times sinus omega t plus phi. Now we go one step further, acceleration as a function of t. That will be first derivative of velocity over time, means that we take derivative already from expression for the velocity. So this minus will stay here. We will get one more omega because we still have this omega t in the argument of sinus. That will be omega square times a, and this will be cosinus omega t plus p. So with this set of equations, we have all kinematic equations for simple harmonic motion of some particle. We have position as a function of time, velocity and acceleration also as functions of time. Since sinus and cosinus functions, they change in the range from their values, change in the range from 0 to unity, then all of these parameters, position, velocity, and acceleration, will possess some maximum values when subsequent like respective trigonometric function cosinus or sinus will reach its maximum value of unity. And that maximum value of these parameters will be defined by coefficients in front of sinus or cosinus. So for x maximum displacement, that will be a, which is our amplitude value. For v maximum will be omega times a, and that is, if we take into account that substitution which we made, that is square root of k divided by m times amplitude a, and a maximum will be omega square times a. So here we will get rid of this square root. So it will be k divided by m times a. So that these are expressions for the maximum extreme values of displacement, velocity, and acceleration. One more thing we need to consider for today is the period of this motion. So there is some capital T, and that is time interval during which the particle goes through the whole cycle of simple harmonic motion. So that means that three of these parameters, displacement, velocity, and acceleration, which are of this particle, which are defined at some phase constant omega t plus phi, some arbitrary phase constant. Their values will be the same for another phase, which will be omega times t plus capital T, which is period, plus phi. So this is another, like, let's call it phase 2, and this is phase 1. So if we have phase 2, which is defined as omega times t plus period, then we can claim that at both of these phases, values for x, b, and a will be the same. In other words, we can write that omega times t plus period plus phi, let's take it in this square brackets, minus, so it's our second phase, minus first phase, and that will be omega t plus phi, will be equal to 2 pi. That will tells us that the whole cycle is finished. And from this equation, assuming that it's equal to 2 pi, we will get that omega times t is equal to 2 pi. Means that the period is equal to 2 pi divided by omega, which is angular frequency. We know that omega is equal to square root of k divided by m. And if we substitute now instead of omega here, we will get that period of simple harmonic motion will be of this system spring block, isolated system, will be equal to 2 pi times square root of m divided by k. Another parameter which is also quite often used is frequency. So there is some frequency is reciprocal to period t, is 1 over t, means how many full cycles of simple harmonic motion can fit in the time interval equal to 1 second. And that is equal to 1 over 2 pi times square root of k divided by m. So now, if we summarize, we introduce the necessary condition for simple harmonic motion when acceleration is proportional to the displacement and its orientation is opposite to the displacement. Then, based on this equation, which relies which defines acceleration with mass and spring force, by setting the differential equation for this simple harmonic motion, we solved it and applied boundary conditions to get the explicit form of position displacement as a function of t. So this is this equation. Then taking first and second derivatives, we got expressions for velocity and acceleration of the particle which undergoes simple harmonic motion, and define also maximum values for all parameters which can be reached under given conditions, introduced the relationships between the period and frequency of simple harmonic motion with the parameters of the system we deal with, so that is mass of the block and spring coefficient K. So with this, that's everything what I wanted to discuss during today's meeting. And if you have any questions, you are welcome. So we will continue working with oscillations further during this week, and in particular during our next lecture, which will be on Wednesday. So please don't miss it, and hope to see you there.
Okay, thank you.
Okay, thank you very much for attention. Have a good day. Take care and see you on Wednesday. Bye.
Thank you. Bye.
Thank you. Goodbye.
Thank you. Bye.
Thank you. Goodbye.
Thank you. Goodbye.
Bye bye.